So in the previous class we discussed about the magnetic field and the force experienced by a moving charge particle. And we also discussed about different type of cases, some special cases, and when the force will be maximum, zero, and a minimum. So now we'll discuss about the definition of the magnetic field. So last class we told one definition, that the space or region around the current carrying conductor within which its influence can be felt by the magnetic needle is called the magnetic field or the of the current carrying conductor. So that we discussed in the previous class. Now here we'll find out some different type of definitions. So already we know that Fm is the magnetic force is equal to QVB sine theta. Now from there we will find out the B. So B will be equal to Fm by QB sine theta. Okay. So here Q is the charge on a particle. Q is equal to charge of the particle. V is equal to velocity, and F is the force. Okay, and B is the magnetic field. Now, if Q is become 1 coulomb and V will become 1 meter per second and theta is 90 degree, then what you can write, if you put this value in this equation, so we'll get B is equal to F into M. So that will get. So magnetic field will be equal to the force. So from this concept, we can write a definition of the magnetic field. So what is the definition? The magnetic field at a point, right? Magnetic field B at a point may be defined as the magnetic force experienced by a unit charge moving with unit velocity at right angle to the magnetic field. So that is the formula. So that is the definition of the magnetic field. So you can write when Q is 1 coulomb, velocity is 1 meter per second, and theta is equal to 90 degree. Then the magnetic field will be equal to the force, or the force experienced by the charged particle will be equal to the magnetic field. So that is kind of definition we can write for the magnetic field. Now we'll go for the dimension of the magnetic field. So this bracket is known as the dimension of. The dimension of B will be, this is force, force, dimension of force, and then dimension of charge, and then the dimension of velocity. So what is the dimension of force? ml to the power of minus 2. Dimension of charge is 80, and dimension of velocity is L to the power of minus 1. So if you do some calculations here, so you'll get M L0, L will get cancelled, L0 to the power minus 2 and A to the power of minus 1. So that is the dimensional formula for the magnetic field. So already I told you the magnetic field is a vector quantity. So now what will be the SI unit of magnetic field? SI unit of B is given with the name of a great scientist, Nikola Tesla. So the SI unit of magnetic field strength, you can write is magnetic. You can write SI unit of magnetic field strength is equal to Tesla. As it is the name of a scientist, so you have to write in a small letter. If you want to write in a short form, then you have to write in a capital T here. Tesla. So what is 1 Tesla? So 1 Tesla is equal to 1 T is equal to 1 Newton by 1 Coulomb into 1 meter per second. Now if I bring the second here, then you get 1 Newton 1 Coulomb by 1 second into meter. What is Coulomb per second? Coulomb per second is nothing but ampere. So 1 Newton is 1 Newton by 1 ampere into meter. Or you can say Newton meter to the power minus 1 ampere to the power minus 1. This is also known as Tesla. Okay, this is also Tesla. Now if question comes, what is 1 Tesla? So 1 Tesla is the magnetic field of a conductor of unit length carrying the unit current and experiencing a force of unit Newton. Okay, so this is the 1 Tesla. Now I'll go to the Cgs unit of the magnetic field. Cgs unit. So what is the Cgs unit of magnetic field? That is called Gauss. So 1 Gauss, remember this formula. This is also name of a scientist. 1 Gauss capital G is equal to 10 to the power minus 4 Tesla. Okay, so these are the things we're going to learn today. Now we'll tell about the magnetic field has like many properties the same like the electric field. So that we're going to discuss now. So the magnetic field is a vector quantity like the electric field E. Okay, and like it has a three-dimensional reference like electric field. So next one is that it can be time dependent like the electric field. And one more thing you remember that the magnetic field depends upon the permeability. It's a very important one, so remember this. The electric field depends upon the things. This one is called permittivity. Okay, this is called permittivity of the this one is the permittivity of the free space. So this is permittivity. But in case of magnetic field, you will learn this one, mu naught or mu. That is called permeability. Permeability. Okay, so one is permittivity, another is permeability. So permeability will be for the magnetic field. So now next one is that same like superposition principle already we discussed in the electric field, that the net magnetic field strength B of many sources at a point is the vector sum of the magnetic field due to the each source like B1, B2, B3. Okay, so if I take different type of magnetic, like different magnetic sources are there, then we can apply the superposition principle. So you can write B vector is equal to B1 plus B2 plus B3 and so on, like this way. Okay, so these are all the basic like things we didn't learn from the magnetic field, and next class we'll continue with the Lorentz force. Okay, so thank you very much.